on the UK side, where me working in collaboration with Carmine Galasso and also John McCloskey from Edinburgh, and also Mark Nadler. The idea is to conduct physics-based ground motion simulation for potential earthquake scenarios in Kathmandu. I will also be short here. There are lots of scientific discussion details that will go into these models, but we have started with the simulation of magnitude 6 under the Kathmandu Basin, and this is where the initiation point of the rupture is placed, and it's based on judgment that these surfaces here have the potential to rupture, and this is the work that has been started in a sense that we will conduct simulation on the order of hundreds in order to encompass different types of ruptures that could occur, and also different locations of the rupture. So for this example rupture, the magnitude 6 has been considered, and these are the rupture area you can see, and with a dip angle of 7, which is more or less close to the dip angle of Gorka event. And the surface that you can see here, the thrusting surface, and what you can see here mainly is the amount of energy that will be released in a magnitude 6 event, a realization of magnitude 6 event, meaning that magnitude 6 event at this location could occur with different realizations of energy release. So, and we will encompass we will encompass most of those possible perturbations of the energy release by conducting simulation for different realizations of kinematic ruptures. And this shows how the rupture propagates in time from the initiation point to the corners of the rupture plane. For the purpose of accurate modeling, since the city work on the Kathmandu Basin geometry, as I mentioned, based on JICA report, has been still going on. I have digitized the JICA report using a very approximate approach, where I have placed the contours on the report output file, and this is the roughly shape of the basin in the Kathmandu, with the maximum depths of around 700. For the velocity profile of the Kathmandu Basin, I've considered this 1D profile for the velocity of primary wave and secondary wave and density. This is based on the validated work that Bijuk Chen has done for the strong motion recording stations in the Kathmandu Basin, and also Ayub has used it for similar simulations in the Kathmandu Valley. I guess with the absence of the more data that will come through the passive seismology work, these are sensible assumptions that I have made for the simulations. For considering the 3D model, 3D simulations of the seismic waves, this 3D hexahedral mesh has been generated. The mesh size is around 1,100 meters, but the spectral element degree of 4, meaning that 5 points of integration has been put inside those elements. So the spatial resolution of the model is fairly, I would say, very good in a sense. And the geometry of the Kathmandu and the basin has been considered. The basin geometry is coming from this model, and topography of the region has been considered through the SRTM database. The 1D velocity model for the cluster layer has been considered based on the Mahish et al. 2013, which this model has been used extensively in Nepal for earthquake location assessments, but it's also consistent with Broker has presented for California. So these profiles has been utilized in the simulation. The outcome of putting together all of these models is to conduct a rupture initiation and the propagation of the waves. And what I'm trying to show here is the surface movement it's a displacement of the ground in the y direction, in the north-south direction. And what I have highlighted 2 points here. One of them, this one on the right, is placed in the somewhere in the middle of the, close to the middle of the basin, where we are expecting to see more of high period, low frequency ground motion, in addition to reverberation that you will see at the tail of the ground motion, versus the one closer to the edge of the basin, where the station, the monitoring station, is placed on the rock, and the amplitude of the motion and also the duration of the motion in terms of the reverberation at the end and significant duration is supposed to be small. And this type of simulation is actually showing that kind of behavior. What you are seeing in terms of color is, as I said, is the displacement in the north-south direction. The rupture starts and the seismic waves are propagated, and the red colors are positive, and it means that in the north direction, and the blue ones in the south direction. So you can imagine the earth is shaking as the rupture is progressing on the fault plane. One important thing that is evident from this simulation is coming up actually is the continuous reverberation, ongoing reverberation of the basin, the layers above the basin after the rupture is finished, which is shown here in this trailing reverberation. Plus, as you can see here, after the seismic event is finished, seismic waves are propagating outwards, and these reverberations that you can see here, this red-blue colors here that are changing, is due to the soft sedimentary layers, soft properties of the soil and sedimentary rock that is placed inside this basin area. So this type of modeling, when we talk about physics-based simulation and why that is more advanced compared to the conventional approach of empirical ground motion models, is actually shown here as one of those points that you would be able to explicitly model these. And imagine if you have a structure here, there, you can assess the performance of and the damage to the structure using these ground motions, and obviously that ground motion that you will use for the structure here will be different. So this type of physics-based models are capable to incorporate the region and site-specific details of the seismic hazard. So at the end of this type of exercise, you would be able to get some ground motion maps. So these maps will be useful for the next step of engineering loss and risk assessment, and subsequently social risk assessment. So what you're seeing here is the peak ground acceleration, peak ground displacement of the ground in the north-south direction, where you can see that this shape is actually following the shape of the basin, in a sense that in the basin area, the displacement will be higher. And this one over on the right is showing the peak ground velocity of that. I didn't present the peak ground acceleration because of the fact that this type of simulation is valid up to, based on the investigation that I've done, up to 2 Hertz mostly, but the peak ground acceleration is affected by more high frequency, around 10 Hertz and more. Because of that, I haven't presented that. The additional work that is going on is to incorporate the stochasticity of different components in order to have a reliable estimates around the peak ground acceleration, which I think is usable for the type of vulnerability assessment that has been going on. Probably Ramesh will present something about this. And these are the other contents of the ground motion. This is the spectral acceleration for 1 second structure, you can imagine. And this is for 3 second structure. Obviously because of the deeper structure of the basin, the low frequency content of ground motions are more affected. So high amplitude you will see here in this region as opposed to the rest. And my intention to put this output here is to indicate the idea that these types of modeling will produce the ground motion animations that you saw, and also the ground motion spatial maps that you are seeing here, in order to be used for the loss assessment. The important point is that for the purpose of loss and risk assessment, the uncertainty in different components of the hazard, including the source, the rupture that I showed in the first slide, and the velocity structure in terms of the velocity profile and the shape of the basin will be incorporated. In terms of the next step, a wider region will be considered. So this only encompasses Kathmandu Basin, but the aim is to grow and encompass entire Nepal. And working with the city team, we will need to incorporate 6 other basin into the model in order to encompass different locations. But Gorkha will be prioritized in a sense that the tomorrow cities is focused on the Gorkha region. For each magnitude that we will consider, at least this is for the first phase of the work, from magnitude 5 to 7, 10 slip realization will be considered for each of those events, and we will compare the outputs with the conventional approach that has been going on in Nepal, which is using the NGA-based ground motion models and some ground motion models from Japan, empirical models that are built based on the data somewhere else for the purpose of use in generic locations mostly, but also in some specific locations. So though none of those models are specific to Nepal, the idea is to utilize physics-based ground motion simulation to represent the characteristics of the hazard, seismic hazard in Nepal, and also compare with the conventional approach in order to highlight the inadequacy of any of these models, most likely an inadequacy in not representing the site region-specific characteristics through the empirical approach. We will need to do validation for a set of recorded events that are chosen. And the final step would be to curate the output in a way that is usable for the risk assessment step that, as Carmina highlighted, will start based on the outputs from the seismic hazard and other hazard. So we are working on a technical paper on the simulation, and the idea is to highlight the fact that these types of simulations, even though there is not much data in terms of various aspects of the physical models, from the geophysical aspects, from the source modeling aspects, if you are giving the task of building a structure there, you need to understand the hazard, you need to use a model to estimate the ground motion. So the discussion in this paper would be around what kind of tools are available, what kind of tools need to be developed in order to conduct reliable assessments of seismic hazard in regions, for example, like Nepal, that we don't have much information, as opposed to regions, for example, like New Zealand or California or Italy and so on. So that would be the focus of this technical paper. Would be great to